Certain periods are marked by dramatic new discoveries or far-reaching new theoretical ideas, although history tells us that science develops in a continuous and comparatively steady way. One of these crucial periods was the 17th century, when modern science was born. Revolution began in the fields of astronomy. In 1543, the Polish astronomer Nicholas Copernicus published his book on the revolutions of the celestial spheres. He proposed that sun and not the earth is at the center of the universe and all planets revolve around the sun, replacing the old astronomical system of the Greek astronomer Claudius Ptolemy of Alexandria. This theory was perfected by Johannes Kepler in the early 1600s based on the work of Tycho Brahe. Galileo provided convincing evidence for the Copernican system of the universe. Galileo's fame rests on his having pioneered modern science through his studies on the motion of the bodies. This revolution started by Galileo was completed at the end of the 17th century in England by Isaac Newton, probably the greatest scientific intellect of all times. Through mathematical techniques devised by himself, Newton formulated his three famous laws of motion and the universal law of gravitation. This was the first synthesis in the history of science and represented the culmination of the scientific revolution. In the 18th century, physicists and mathematicians greatly developed Newton's work. Theoretical mechanics developed in the wake of the Principia, whereas the experimental nature of the optics influenced the science of electricity, magnetism, and light. In the 19th century, the science of physics developed rapidly. Early in the 1800s, experimentalists proved that light propagates as waves. In the mid-century, it became understood that heat is a form of energy, thereby assisting the evolution of the new science of thermodynamics. Electricity and magnetism, until then seen as two distinct phenomena, were found to be manifestations of one and the same unified electromagnetic field. Their mutual interaction was beautifully synthesized in a set of mathematical equations by James Clerk Maxwell. Maxwell's great synthesis of electricity and magnetism represents a milestone on the road towards the goal of the ultimate unification of the forces of nature. But in spite of many accomplishments in the field of classical physics, a number of vexing problems still remained unsolved. This included the question of the potential existence of a medium through which light propagates, the lack of real understanding of cathode rays and atoms, etc. Towards the close of the century, a flood of discoveries swept in. These included X-rays, radioactivity, the electron, and new radioactive elements, bringing about a veritable revolution which opened the door to 20th century physics. On 10 December 1901, at the Royal Academy of Music, before the King of Sweden, the first Nobel Prize in Physics was awarded to Wilhelm Röntgen for the discovery of X-rays. During the period 1901 to 1910, the Nobel Prizes highlighted achievements in the late 19th century. Of the 10 prizes, 2 went to inventions and 7 to experimental discoveries. Among them are X-rays, radioactivity, the discovery of the true nature of cathode rays, and new features regarding the atomic spectra. At the Frederick Wilhelm University, Max Planck, professor of theoretical physics, made a great discovery that solved the black body problem and actually produced a revolution of ideas which marked the dawn of modern physics. Planck supposed that the atoms absorb the energy that is carried by the waves only in individual packets or quanta, and the energy of each quanta had to be related to the frequency of the wave. The quantum concept was to become the basis of a new theory, the quantum theory, which explained all the phenomena of the atomic and the subatomic world, and developed into one of the most revolutionary concepts in physics of the whole 20th century. So the year 1900 can be considered the birth of the quantum era, and Max Planck recognized as its father. He received the Nobel Prize in 1918. The year 1905 was an exceptional year. A German-born Swiss physicist named Albert Einstein was working at the Swiss Patent Office in Bern. He published at the age of 26 2 revolutionary papers in the Annalen der Physik. In the first paper, Einstein advanced a hypothesis that light consists of quanta of energy which travel through space. He maintained that such quantum properties are inherent in the nature of light itself. Einstein demonstrated the effectiveness of his light quanta hypothesis in explaining the photoelectric effect. The other paper bore the title On the Electrodynamics of Moving Bodies. In this paper, he elaborated his special theory of relativity, which sparked off a revolution in physics comparable to that in astronomy brought about by the ideas of Copernicus, Kepler, Galileo, and Newton. Einstein was awarded the Nobel Prize for Physics in 1921 for his services to theoretical physics and especially for his discovery of the law of photoelectric effect. However, he never received a Nobel Prize for his theories of relativity. After developing a special theory of relativity, Einstein turned his attention to gravity. In 1907, he published a paper reviewing relativity. He set out his principle of equivalence. During 1915 to 1916, Einstein came out with his general theory of relativity, a completely new view of gravitation, with his paper entitled Foundation of General Theory of Relativity. These theories of special relativity and general relativity played a central role in the development of the 20th century physics. His contribution to quantum theory, apart from light quanta hypothesis, included the concept of stimulated emission in atoms and the development of Bose-Einstein statistics. Later, his interest centered on the search for unification of electromagnetism and gravitation in what came to be called a unified field theory, which remained for the rest of his life an unsuccessful quest. Einstein died on 18th April 1955 at Princeton. In other developments in quantum physics, the Danish scientist Niels Bohr published his pioneering papers on the constitution of atoms and molecules. Using Rutherford's nuclear atom and Planck's quantum theory, Bohr worked out a revolutionary model for the hydrogen atom that was successful in explaining spectral lines. Frank and Hertz secured important results through the famous Frank-Hertz experiment, which confirmed Bohr's hypothesis of quantum excited states of the atom. Arnold Sommerfeld carried out important research on the structure of atoms. He advocated the theory of elliptical orbits for the electron and thought of the quantum states of the atom as being characterized by 3 quantum numbers. With his theory, he was able to explain the fine structure of hydrogen spectral lines and also the Zeeman effect. The second wave of quantum revolution arrived exploding in a flurry of discoveries. During 1922 to 1923, Arthur Compton got experimental evidence of the existence of the light quanta. In 1921, Louis de Broglie put forward his bold idea of matter waves. During 1925 to 1927, an entirely new mechanics called quantum mechanics was formulated by Werner Heisenberg, Erwin Schrödinger, Paul Dirac, Max Born, Wolfgang Pauli and others. Pauli proposed that a 4th quantum number was necessary to identify the quantum states of the alkali atoms. This led Uhlenbeck and Goldsmith to publish their ideas of a rotating electron. To understand the structure of all other atoms with more than one electron, Pauli introduced the exclusion principle. Heisenberg's paper entitled Quantum Theoretical Reinterpretation of Kinematic and Mechanical Relations is one of the foundation stones of modern physics. Later in 1927, he established the uncertainty principle. Schrödinger introduced a theory describing the behavior of particles by an equation known as Schrödinger equation. Both Schrödinger and Heisenberg, from different starting points, created a comprehensive theory of quantum mechanics that reproduced all the positive results of the old Bohr-Sommerfeld theory. Another key individual in the quantum revolution was Paul Dirac, who reformulated Heisenberg's matrix mechanics in a new form. In 1927, he published a paper in which he laid down the foundation for quantum theory of radiation called quantum electrodynamics. Dirac's electrodynamics was completed during 1929 to 1930 by Heisenberg, Pauli and others, and in 1940s the theory developed into its present modern form. Other major discoveries in the first half of the 20th century included the discovery of superconductivity by Kamerlingh Onnes in 1913, the discovery of wave-like characteristics of X-rays by von Lau, which got him the Nobel Prize in 1914, and the unraveling of the crystal structure by Bragg and Bragg using an X-ray spectrometer. In 1930, the Nobel Prize for Physics was awarded to Sir C.V. Raman for the discovery of the phenomenon of Raman effect. The 30s also witnessed the construction of the first machines capable of accelerating subatomic particles to very high energies, the discoveries of deuterium, positron, neutron, and also artificial radioactivity, opening up a new world of high-energy physics. There were a wave of inventions in the 1950s. The transistor, which was invented at the end of 1947, had a strong impact on 20th century science and technology. This was followed by the invention of the maser, laser, IC, nuclear reactor, radar and phase contrast microscope. These generated in the following years a flood of new technologies which transformed science and many aspects of everyday life. The scientific boom of the 50s continued during the 60s. The first artificial satellite, Sputnik 1, was launched by Russia in 1957. Later in 1969, the US astronaut Neil Armstrong landed on the moon. The period following the 50s saw huge advances in our knowledge of the cosmos. Amazing discoveries were made, which included the quasars, the first X-ray cosmic source, the cosmic microwave background radiation, and the first pulsar. In the year 1965, the Nobel Prize was awarded to three theoretical physicists, Richard Feynman, Julian Swinger, and Tomonaga, for fundamental contributions made towards the development of modern quantum electrodynamics, or QED, the most precise theory of electrons and EM radiations. The decade of the 1970s saw exciting developments in the knowledge of the subatomic world, including the evidence of the existence of quarks within protons and neutrons and discoveries of new particles. General relativity became one of the most active and exciting branches of physics. Astronomical discoveries, example black holes and the first binary pulsar, demonstrated that general relativity would have important applications in astrophysics. The phenomenon of superconductivity was explained by Bardeen, Schiffer and Cooper through their BCS theory. The 1979 Nobel Prize was awarded for one of the crowning achievements of 20th century physics, the merger of two of the four fundamental forces of nature, the EM force and the weak nuclear force, into a single theory, the electroweak theory. Spectroscopy, an old science, was developed further in the 80s. The discoveries of the top quark and tau neutrino have to be seen as achievements of a very long journey that started off more than 40 years back in a continuous and widening search for the ultimate building blocks and the most basic forces of nature. Physicists are working towards devising a final theory which would unify all the forces of nature. During the preceding decade, stars, galaxies and the Big Bang have been explored, and the results have revolutionized our understanding of the universe. Advances and breakthroughs in the physics of matter and light, superconductivity, superfluidity, NMR, etc. have had an enormous impact on science. Modern electronics has led us into the information age. New promising lines of research have opened up. The ability to manipulate superchilled atoms yielded in 1995 a new state of matter, the Bose-Einstein condensate, and opened the doors to the development of new quantum technologies. This inquisitiveness has brought mankind this far. The quest is unending. The glory of the past will live for eternity.